We're an institute of computational scientists, and they're like biologists and quantum materials people. So we have a seminar for sort of just the whole institute, and so I gave this talk in January on planet formation, which is what I sort of specialize in. And I thought it'd be fun to sort of rather than talk about specifically things we really know about, to say more about what we don't know about, what are sort of the open questions, right? So I'm going to go through this here, and yeah, feel free to jump in with questions. We don't have to cover all the stuff I've got. There's not that many slides and so forth. So maybe to start with, I would like to sort of frame this in terms of, okay, what are the things we would like to know about planet formation, right? And over the years, people have sort of thought about that, I think, in different ways. So one way, which actually, a few years back, or quite a few years back now, NASA was like really keen on, was to sort of frame a lot of like NASA science and astrophysics in terms of a sort of origin story, right? And in that picture, sort of, there's the early evolution of the universe, there's like the really big picture stuff. There's the origin of life on Earth. There's another part of that story, and then the part in the middle is sort of the origin of the Earth, right? And that's planet formation. So I think the first thing I would just like to say is that, since this is going to be a talk about things we don't know, the sort of big picture view of like, how the sun and the Earth came to be, right? I would say is sort of understood at sort of the level that you find in like undergraduate astro textbooks, right? So, plenty of stuff is sort of basically firmly known and can be sort of accepted as fact. However, more recently, but still now like 25 years ago, the first exoplanets were discovered. Right? And as sure everyone knows, the first exoplanets that have been discovered, and many of the ones that have been discovered since, those planetary systems don't look at all like the solar system, right? The prototypical example was 51 Peg, which Didier Queloz and Michel Mayor got the Nobel Prize for, and that's like a Jupiter-type planet in a few-day orbit around a basically solar-like star.
First question: our techniques for detecting exoplanets are biased towards detecting and large planets close in. So, if there are a lot of solar system-like exoplanets, have we just
yeah. So that's an excellent point. So I guess we sort of go back to 1995, right? There was like no knowledge about that question at all, right? And actually, indeed, the hot Jupiters, like the very first one, are a pretty rare kind of example, right? So they're not very common, and we still don't know how common solar system like analogs are, right? Or even Earth analogs, never mind solar system analogs. However, what we do know is that since then there was NASA's Kepler mission, which detected several thousand planets, and something that was discovered there is that the close-in planetary systems, but not now giant planets, but more like 5, 10, 20 Earth mass objects, those are sort of present around on average roughly a 1 per star, right? And we know that giant planets like Jupiter are probably at like 10% level. So in that sense, we know the solar system isn't the most typical thing, because the most typical thing has something closer in. So yeah, we'd need to have a proper Vulcan or something to be like in the most typical class. So we know that. So we know that the solar system is not the most typical kind of thing. But what we still don't know is, is it a little bit atypical, right? Just a bit off the distribution, or are the features of the solar system that are actually somewhat uncommon, or maybe even really uncommon among planetary systems? And observationally, because of the bias issues of the various techniques, we don't know that, right? And in the sort of, I would say, the most current way of thinking about things, the thing people are focused about looking forward is trying to measure planetary atmospheres and say something about planetary habitability, and perhaps the possibility of like measuring something in the atmosphere that is characteristic of life, right? And so that's what, that's the direction people want to go in like the next 10, 20, 30 years or whatever, right? And from a sort of theory point of view, what we would maybe like to work out then is is the composition of planets and how they're built up similar to how we think it happened in the solar system, which we know has had a favorable outcome on the Earth in terms of habitability, or is it characteristically different? Okay. So that's a little bit of an abstract way putting it. So I think it's useful to think about like a specific example. And the example I like to give is the question of the Earth's water, right? Because the water on the Earth is sort of the most basic thing we know about the Earth that makes it habitable. So there's like tons of things people talk about that, you know, make the Earth habitable, like the presence of the moon, magnetic field that shields us from the solar wind and stuff like that. But the water is, you know, the most basic thing that I think, you know, pretty much everyone agrees on. And this is actually pretty simple, right? And it just really requires like one piece of physics. If you're at low pressure, so planets formed in low pressure environments, very low pressure, basically what we would call a really good vacuum on Earth. The stable phases of water are ice and vapor, and you can't have stable liquid water. And at the pressures where we think planets formed, that transition between the ice phase and the vapor phase is at about 150 Kelvin, right? So you make a sort of prediction from that if you imagine solid planets like the Earth, they're forming from sort of local material in a disk of gas and dust around a young star, they should have a temperature-dependent composition. So if they form close to the star where the temperature is above 150 K, the water will be in the vapor phase. So it won't tend to get accumulated in minerals that ended up being in the planet. If you're further out, it'll be in ice, and hydrogen is super common. Oxygen is also a common element in the universe. So you actually will have a lot of water ice in places where it's cold enough to have that water ice. So then you'll get a planet that in principle could be a half or even 2/3 by mass made up of water, a sort of so-called water world, right? So that's what you would sort of predict. And the other thing you need to know is, okay, when the planets were forming, you know, the sun, proto-sun was there, and it had a bit different luminosity to what it has today. But the temperature of material at the location where the Earth would become is still basically set by the same balance of sort of heating from solar radiation and then radiation back into space as sets the temperature on Earth today. So very roughly, the temperature in the disk where the Earth would have been forming would have been 300 K. So that's, you know, that's comfortably more than 150. And so the prediction would be that the Earth formed inside the so-called snow line and it wouldn't have water, right? And of course, you know, you look at the Earth, that's not what we see, right? So this simple prediction based on like really simple physics is kind of not very good, okay? So I don't want to belabor the point. For the Earth, we sort of know the answer to this conundrum, right? And it's a long story of its own in planetary science. And the key thing is that we can measure the ratio of deuterium to hydrogen in the Earth's water, in the ocean, which is the main reservoir we have access to. So deuterium is heavy hydrogen. And we can compare that to various possible sources in the solar system where the water could have come from. So, you know, you might immediately say, well, the obvious place it could have come from is comets because they contain a lot of water, right? But the majority of comets do not have a D to H ratio that matches what we actually see on the Earth. And the stuff in the solar system that we've measured that does have the right D to H ratio is meteorites that we know came from the outer region of the asteroid belt. So probably the sort of standard picture is that the Earth's water came late after most of the Earth had been sort of formed, and it ended up here due to like complicated interactions with Jupiter and Saturn, got sort of scattered that stuff inwards from the outer asteroid belt, and then it hit the Earth. Okay, so that's something we know about the solar system, and you know there's more to it than I've just said, and people still debate even quite basic things about where the water came from, but that's the standard story. But there's a sort of lesson here for understanding planet formation and exoplanets more generally. One is that you really should think about the planetary system as a whole, not like individual planets, because in the solar system, the Earth's habitability really crucially depends on this complicated chain of processes that involve the asteroid belt and Jupiter and Saturn. And so, you know, again, going back to that question of biases, you know, we know some sort of candidate planets that might be Earth-like around other stars, but we don't generally have a full understanding of what those planetary systems look like. You know, do they have planets further out? Do they have asteroid belts and stuff like that, right? And then the other point is that in the solar system, at least, even pretty basic things about habitability are actually not so simple, right? It's not just a matter of working out what the temperature on the planet might be. you really need to know, in principle, the whole history of how those planets came to be. And if you don't know how the system formed, it's sort of hard to have a reasonable guess, really, what the planet might look like. Okay, so that's sort of the motivation, I guess, for what we do. Okay, so let's then move on to sort of just the basics about what we do know about planet formation. And one thing we know quite well is the environment, and the environment is systems we call protoplanetary disks. And this is a composite image. So this is a disk around a young star. You can see the scale bar there. So we're looking at something that's sort of, roughly speaking, the size of the solar system, sort of going out to the Kuiper belt. And the sort of orange-red colors are observations made in millimeter and sub-millimeter wavelengths. And so there you're looking at dust in the disk around the star. And so you get this pattern of rings, which I'll sort of come back to. And then the blue stuff is shorter wavelength emission, which is showing a jet probably produced very close to the star. So this is the environment in which planets are forming, and we know something, about the temperatures and the densities and the masses and so forth of those disks. Right?
We're not seeing the
mostly
slides.
gas, but they have like 1% or something by mass of solid material, which would be like things like silicates and ices, and that's ultimately the building blocks of the planets. And we know that they live. The lifetime is about 3 to 5 million years. So it's a really short fraction of the age of the Earth or the lifetime of a star like the sun. So it's a pretty brief window where you have this sort of conditions where the planets would be forming.
Excuse me.
Now we also have sort of a general picture of how the growth takes place. And it's a sort of bottom-up picture. You start with small stuff and it grows into big stuff.
We are not seeing.
And so if you start with really small stuff, so you start with really dust, so that might be microns in size. Those dust particles grow by colliding and sticking. Okay, and so you're looking here at a simulation which someone did, a Japanese group did. People also study this, in microgravity labs. I think there was certainly an experiment on the space shuttle, maybe an experiment on the ISS. I'm not sure. You take a bunch of little dust particles, let them float around and hit each other. They stick pretty efficiently and form these sort of filamentary or maybe fractal-like kind of structures.
Not seeing the slides.
Icy mantle around.
The slides are not being seen.
That's an excellent question. And it's not completely, the answer is not completely known.
I don't think
most of the experiments have been done actually with rocky materials, with silica grains. So there it's like surface forces.
Philip!
Van der Waals force ultimately. So surface forces between the dust particles.
Mr. Armitage!
Exactly how different
Doctor.
ice particles are from rocky things in terms of their sort of stickiness remains a bit open. So it's known that if you take water ice just below its sublimation point, then it's actually quite a lot stickier than rocky stuff. Right? If you go really far out in the disk, so like where maybe the comets would be forming, then you'd be like way below the sublimation point. Right? You might be like 20, 30 Kelvin. Right?
This is what they record.
Those super low temperatures, it's been argued actually that maybe the icy materials are basically behave just like rocky materials. But that whole thing remains a bit open because it's much harder to do lab experiments on cryogenic ices. So,
Philip!
Yeah, we don't know.
He can't hear us.
Anyway, one way or another, that process we think goes pretty well up to like millimeter or centimeter sizes.
I give up.
So, if you want to ask, well, how do you make millimeter or centimeter things? It's just stuff gliding pairwise and sticking and giving you that thing.
Can't even move them.
So then from millimeter centimeter sizes, the next step, which I'll sort of come back to later, is growing planetesimals. So those are things that are kilometers in size. And this is an image of Arakoth, which was flown by the New Horizons spacecraft in the solar system. And I'll show a better picture of that in a minute. So you make these things that we call planetesimals. And then the basic story is that you make the terrestrial planets by colliding the planetesimals. Planetesimals collide together, and then they may also sweep up the pebbles that are the sort of millimeter or centimeter size things that were left over from the earlier phase. And we make the terrestrial planets that way. For the giant planets, we make sort of bigger terrestrial planet-like things we call cores, maybe of 3 Earth masses or bigger. And then once you get that big, those objects can accrete gas from the disk, and then they can get the envelope, small envelope for Uranus and Neptune, really big envelope for Saturn and Jupiter.
Dr. Armitage, the people at home are not seeing the slides advance. I
Okay.
don't know why that is.
Let's maybe try again. Let's see.
Oh, yeah, what?
Yes, we're good.
We're still seeing the presenter view screen. We're not seeing the slides.
Okay, can people see the current?
Yeah, we're seeing it.
Okay, we'll see if it continues to work.
Sorry.
Yeah, so that's the thing we know. So why is it hard to do better? Why is it hard to learn more? And the basic reason is that the sort of things we can observe only fill like a little corner of the available total range of like scales and time scales of interest. So I've sort of schematically showed it here. You've got time on the bottom axis here and size on the other axis. When we look at these protoplanetary disks, that's the bottom left corner. Those live for like a few million years. That's a short time. And the direct sizes we can observe go up to like millimeters or centimeters. Right? So we can sort of see small solids for a few million years, basically, in that corner. And then, of course, we can see lots of exoplanetary systems. This is a little movie of all the multiple systems that were found by the Kepler mission. So there's a lot of those and many others that weren't multiples. But those are mostly around really old stars. And of course, the planets themselves are, fully formed planets, right? And there's a big space in between, which for the moment is sort of practically not observable, right? So it's very hard to see, or impossible at the moment to see, like 100-meter sized things around a 100-million-year-old star, right? You're not going to see those no matter what you do. So let's then sort of pose these or discuss these questions about things we don't know. And so the first question I want to discuss is a timescale question. When do planets form? Right? Obviously, they have to form early, but how early is early? And the old answer, would be relatively slowly. So what you're seeing here is a computer model of the formation of the Earth and the other terrestrial planets in the solar system. So it's distance from the sun on the x-axis, eccentricity of the orbits on the vertical axis, and what you're sort of watching there was a computer model of a bunch of relatively small objects, initially on sort of circular orbits, that grow and collide amongst themselves and eventually form something like the solar system. So here you're forming sort of a model Earth, a model Venus, and a model Mars, and then there's a few bits left over in what today would be the asteroid belt. And then near the front, you can see the time unit there. The prediction here is that took like 100 or 200 million years to go to completion. And that's, for the solar system, that's not a bad number, because the sort of standard thought about when the moon was formed, maybe the formation of the moon was like one of the last big collisions, the last big collision that was experienced by the Earth, maybe places that 50 or 100 million years after the earliest events in the solar system. So that seems all right. For giant planets, we've got to do things more quickly than that, because we've got to get the gas before the gas disk gets blown away. And I mentioned before, that takes like a few million years, 3-5 million years, something like that, right? But again, the sort of old picture of that is that building Jupiter at Jupiter's location takes most of that time you have available, right? And in fact, the sort of standard story people used to have for, why is Saturn not as massive as Jupiter? And then why are Uranus and Neptune much less massive still, is basically that, those would have become Jupiter, but they ran out of time because they were further away from the sun, right? And that's like an intuitive thing that, sort of makes sense and is consistent with what we see. However, in the last 10 years, these observations of protoplanetary disks that I've already sort of alluded to have really challenged this view about how quickly planet formation takes place. And the reason is that when you image these disks, so these are radio observations in like millimeter, sub-millimeter wavebands, what you see is that most of them, the great majority of them, have some kind of substructure in them. And the most common kind of substructure is that they show rings, okay? And this was not expected, right? So it was expected that you would see sort of a smooth distribution of dust and gas in these disks when you could actually image them. But instead, they show rings. So the one over here, HL Tau, is the original and maybe the most famous example. You can see multiple sort of concentric rings. But then some of these other systems show other sorts of things like sort of spirals and crescents and various other kinds of substructure, right? So that's what we, actually see. Yeah.
You go back to that.
Yeah.
So since we're imaging in those wavelengths, are we saying that we're seeing radiation coming off of solids, or what is it that we think we're physically seeing in that ring?
Yeah, so these images, I think all of these images are so-called like dust continuum images. So they're like broadband millimeter wave things. So we're seeing dust, but large dust. So we're seeing like basically millimeter sized particles. So that's really what you're looking at here. There are also images in scattered light, which is like probing much smaller dust particles. And then there are other radio images that look in molecular emission, mostly carbon monoxide, where you're looking directly at the gas.
So let me ask it differently. Is the emission that we're seeing the result of particle friction, or is this the light that's coming off the star that we're seeing reflecting off the particles?
Almost a second. Okay. But it's more actually like the starlight is being like absorbed by these dust particles and then re-emitted at much longer wavelengths.
Okay,
Noticing that most of these are in the same range between 400 and 600 light years from Earth. Is that a limitation of how we're looking? Or, I mean, I see one that's an anomaly at 194, but do we see closer or we see?
Yeah, so this is basically just saying where are the nearest star forming regions to the Earth, right? And so the nearest is like 150 parsecs light years, I guess it's given here, right? So that's like some TW Hydra is like the nearest disk we see. The nearest place where we see like populations of disks would be like in the Taurus star forming region and a few others like that. And those are, more like 450
But that's
light
not
years.
a limitation of power view.
No, though, of course, there are tons of disks that we know about further away, and those just look smaller on the sky. And so you can't really image them. So these are the easiest targets, basically.
Still no slides.
So why is that a problem? Well, so it's actually long been known that rings and spirals in disks can be formed by planets, right? And so actually, so I wrote a textbook on planet formation, and in the first edition, which is 2010, the picture on the front is a simulation of a planet interacting with a gas disk, and you can see it makes like a ring of low density material, a gap, and then it creates like a spiral, right? And then the second edition was that HL Tau image. And if you kind of, blur and use imagination about the color scale, hey, it doesn't look so different, right? So that actually sort of sounds good, like a bit of theory that appears to be finding support from observations. But the problem is that the observed rings are seen really far out, right? So actually, coming back to the question there, we still can't really observe these disks on scales that sort of correspond to, like, say, the terrestrial planet region, and even Jupiter is pretty tough, right? So most of these rings in that previous thing were actually more like 50 or 100 astronomical units away from their stars. And they also include disks that are really young. So ones which we're pretty sure the star is less than 1 million years old. So in the sort of standard picture, planets just shouldn't form there that quickly, right? In fact, at 100 AU, they shouldn't form there at all, because like in the solar system, clearly we've not got anything out there at 100 AU. I mean, there's maybe planet, whatever it is, planet 9 or 10 or whatever. There's that story, but let's not go there. So in classical theory, at least they shouldn't be there. So there's a puzzle there. If those structures really are due to planets, how did the planets get there so quickly? So we don't know. So the basic point is we don't know what's going on, right? And it's genuinely we don't know what's going on, right? So this is not a tease where I'm going to say we don't know what's going on and then I'm going to tell you we know what's going on. We really don't know what's going on. But I can give you the sort of three characters of the three types of explanations that might be the answer, right? So the first is kind of maybe the disappointing one, right? It could be that the rings, even though the rings, let's say, could be formed by planets, it could be that something else forms the rings that's got nothing to do with planets, right? So ultimately, the sort of reason we think planets would be a good way to make the rings is that, if you look at Saturn, the gaps in Saturn's rings, we do see moons in those systems that are clearing out here, right? So it seems like there's a really close analogy there. But you could certainly imagine that there are other processes that could make a ring of gas and dust in a gas and dust disk. And the Flatiron Institute where I work, we had a postdoc a few years back who worked on one mechanism for doing that involved magnetic fields. So there are ways that could happen, right? And they're just hard to really calculate and work out in detail how plausible they are. Okay. Then the other explanation, which I'm going to just say a little bit more about, and which I would say is maybe the most, the most conservative, the least risky way of thinking about it, is involving the question of how much of the growth of planets comes from collisions among planetesimals, the kilometer-sized things, and how much comes from sweeping up pebbles. And so there's a story that if you have most of the growth coming from pebbles, you can make things go much faster. Okay, so that would be a different mode of making planets that's kind of a little bit different, I think, to even the basic story that you may have heard about before about making the Earth, right? So it's a pebble-driven story. And then the final possibility, which actually is one that I've been thinking about recently, is maybe you make these early planets in a sort of basically a fundamentally different way to the way we thought we made the solar system planets, right? Maybe that's the most interesting, but it's not clear that that's the right answer. So let me first of all mention this idea of the pebbles as being the key to the solution, right? And the key here is, I said the small stuff grows by just little dust particles hitting each other and sticking. And then from that millimeter or centimeter size, you got to kilometers. But I kind of conveniently stepped over the question of how you in fact get from millimeters and centimeters to kilometers, because that's still quite a big range. And we know pretty much for sure from lab experiments that millimeter and centimeter size things, when they hit each other, they don't tend to stick together too well, right? And a colleague, Doug Lynn, who did a lot of early work on planet formation, years ago, decades ago, used to make fun of people who discuss sticking as the way of making everything by saying, that he would send them out into the Utah desert or something and get them to throw rocks at each other and to come back when they found two of them that hit and stuck, And in the end, that is basically the physical limitation, right? That at least for rocky material, it doesn't stick well once it gets to a certain size. Now, of course, you can also say, which can come back to the question, if you take snowballs and they're kind of mushy snowballs and you throw them at each other, actually they stick pretty good, right? But then again, if you then go to really hard ice, you're back to the non-sticky. So, that's the basic thing. So how do we think we form planetesimals now? So we think actually that this is due to an instability, right? And I'm showing a little movie, a simulation we did of this a few years back. So what you're looking at is a tiny little patch of the disk. R is the distance from the star, and then the other distance is the distance along the orbit. And you start with a uniform mixture of gas and pebbles. And it turns out that mixture is unstable to clumping. And it's actually related to stuff that people study in various engineering applications on Earth. And so the basic story is this sort of clumping could make really dense clumps of pebbles. And then the clumps get so dense and massive that they collapse under gravity, and you build directly the planetesimals. So you sort of skip over all those difficult meter and 100-meter size scales just in one jump under gravity. Okay. So that's not a proven way of making the planetesimals, right? But it's thought to be the most plausible hypothesis for how you make those sized objects. And in particular, New Horizons, the NASA mission, after it went past Pluto, went on to a Kuiper Belt object, which is now called Arrokoth. And it's this thing shown here, and it's a small thing, and it's the best guess we have for something that might be really a primordial planetesimal left over from the early days of the solar system. So, of course, in the asteroid belt, we have lots of small stuff in the asteroid belt, but most of that stuff is collisional fragments from collisions among larger asteroids. So out in the Kuiper Belt, things don't collide very much. And so when you fly by something, there's a pretty good chance that that really has stayed like this for 4.5 billion years. And so, you know, when people flew by this, it seems to have like two bits that appear to have like stuck together. And people have tried to estimate, you know, but it seems that these two pieces came together rather gently, right? And that appears to be consistent with this kind of gravitational collapse story for making the planetesimals. So it's a, you know, it's a model that has some observational support in the solar system. So, you know, for the moment, this is the only object in the outer solar system that we really imaged.
For something like this, you know, I've seen pictures of it before and with no information whatsoever. It looks to me like two things that might have hit hard and welded together. In other words, such heat was formed that a portion of it melted and then bonded. Is that something that's been pretty much rejected?
Well, so yeah, I mean, so I would say, yeah, people have studied the sort of structure of this region around the neck, right? And also like just the density of the objects and stuff like that, right? And they say that it is a relatively gentle impact, right? And probably that makes sense because, you know, these things, even though they sort of look like solid things, they're, you know, these are low density objects, right? So actually it doesn't take a lot to like pulverize them into just lots of pieces, right? So if you really had a high velocity impact, you would break it up into a lot of chunks, and the chunks might actually come back together and make a new object, but then it would be kind of a spherical object.
Okay, so those are not, those are, you said, very low density objects.
Yeah, these are pretty fragile things.
Okay.
But, you know, I should say this is way away from my area of expertise. So I'm only trusting the people who, like, you know something about how these things kind of collide together.
What is the scale of what we're looking at in the picture?
So these are things that's like 10, the bigger thing is like 10 kilometers or something like that in size.
So if we were looking at a region that's at a great distance from us, couldn't there be many, many objects like this that we wouldn't be aware of?
Sure.
We see the dust over a huge range, and it's relatively uniform in the range. But if there were objects at this scale,
yeah,
in there, wouldn't we miss them?
Yeah, for sure, right? I mean, we think there would be such objects, and yeah, we have no way directly of knowing what their distribution is.
So therefore, it's very hard to predict what stage those rings are in terms of accumulation.
Yeah, for certain. Yeah. You know, the only
fact that they seem to be over such a large distance from the stars.
Yeah, the only place where we can learn a little bit is not in these sort of young disks, but we also see things called debris disks, which are around like, you know, older stars, but not super old, right? And there again, we just see the dust, right? But there's no gas, or in most cases, there's no gas in those systems. So the dust in those systems is ultimately getting blown out by stellar radiation pressure on a short time scale. So there, where we see the dust, we know that the dust has to be being continually replenished, ultimately by, you know, collisions of things that are sort of this size. So in some of those systems, again, you see like cavities or rings and things like that, right? And there people infer that the parent population of things like this must have some kind of particular distribution to be what we see. But that's not the disks I was showing before. Those you're completely right. We've no way of knowing what the radial distribution of, you know, 10 kilometer size things actually is. It's completely unknown. Okay, so that's how we think we make the planetesimals, right? Through this kind of collective instability. And so that sort of allows what I would sort of maybe describe as like a just so story for how you might be able to make planets really quickly, pretty far away. And the story would be, well, okay, you form the pebbles first through these like collisions, and that we know pretty well that happens quickly, right? So that's fine. And then you get this instability to make the planetesimals. But instead of putting like all the mass into planetesimals straight away, you just make a relatively small number of really big ones, right? Maybe already hundreds of kilometers in size. So sort of comparable in size to the largest asteroids. And if that's the case, it might be that those objects are already big enough to grow by sweeping up the remaining pebbles and not having to rely on the slow bit, which would be how long it would take them to collide with other big objects. So you could kind of actually, in this story, the pebble growth, which might play a role in the formation of the Earth, would be like the whole part of the story, right? You sort of first of all make a big jump to a big primordial asteroid or something like that, and then the big primordial asteroid sweeps up all the pebbles, and then it runs away to like 10 Earth masses or 20 Earth masses, where it can start to make these structures in the rings. So that's actually it's plausible, but there's a lot we don't know about that, right? And we certainly don't know in any way really what sets the balance between how many planetesimals we form and how much stuff remains left over as small things. So there's still trying to find a way to really answer that kind of question. So then let me just mention then the other possibility, which is to say the one that we've been working on a little bit. If we think about really young disks, so now not 1 million years or 3 million years old, but maybe less than 500,000 years old or something like that, right? The disks we see today typically are pretty low mass compared to the mass of the star. So, actually often very low mass, like 1% or something like that, right? And at tops, maybe 5%, something like that, But presumably at some point, the star had to have ultimately sort of formed probably from the disk. So if you went early enough, maybe the disk had a comparable mass to the mass of the star. And of course, it's very difficult to see that because at that phase, everything would still be sort of enshrouded in the collapsing material that was forming the star and its disk. Okay, but we think that those young disks, should have existed, and they would have the property of being so-called self-gravitating. That's being shown in the simulation here. That just means that the orbits are not just controlled by the gravity from the central star, but also from the gravity of the gas in the disk itself. And when that's the case, you're in a regime that's kind of like a galaxy, and just like in a galaxy, you get spiral arms forming in the gas. And what can happen there is sort of twofold. So first of all, in that environment, the early phase where the particles are sticking, which I said before kind of peters out at like millimeter or centimeter sizes, can go at least, we think, a little bit further than that. So you can make some physically larger objects in the denser and different environment that you have early. Okay, so that's something that we've been looking at. And then maybe more importantly, the spiral arms can sort of act as locations that trap that solid material. So the spiral arms sort of form in the gas because the gas has gravity, but then they're high pressure regions that act as kind of traps for solid material. And that's due to aerodynamic effects of the solids against the gas. And so we've done simulations there, and there's a possibility that the particles collect in the spiral arms until they become dense and massive enough that they can collapse under gravity, now not to form planetesimals, but potentially even to form like things that are getting to a fraction of an Earth mass. So you could maybe make things really quickly in that kind of story. So that's something we've been working on. I would be the first to say we don't know if that story hangs together, right? There's lots of pieces that are hard to observe, that are hard to do simulations or calculations of. So we're still sort of trying to look at that. And on the observational side, there's a lot of work to try to image younger disks, bigger samples of disks, try and say something whether really there are planets there, what their masses are, and that kind of stuff, right? And hopefully, I think in a year or two, on the theory side, it's hard to know how quickly progress will happen, but we know the observations are coming. So I think we will know more about it in the next few years from further observations.
Where did the observations come from? What instrument?
So everything I've been showing pretty much so far has been ALMA. So that's submillimeter in Chile. There are also observations in scattered light, which come from telescopes on Hawaii and the European Southern Observatory. But mostly it's this radio stuff from ALMA. And basically the problem is, so ALMA is the only facility that can do this, and it's like super oversubscribed for time, right? So it's like 10 times oversubscribed for time. So the disks that you've seen already are in fact the brightest disks and the easiest to observe. So to do more disks requires, bigger chunks of telescope time, and it's, I'm not applying for that time, but the people who are applying for that time, it's as you might expect, very difficult to get. So it's a slow process, but it will happen. Okay, so then let me maybe then just say something about one other question, which is a sort of nature versus nurture kind of thing for exoplanets, right? So if you go back to like, the late 90s, when the first exoplanets were discovered, the sort of, I would say the main kind of sort of change in thinking that was prompted by those observations was the view that the planetary systems we see today are substantially the result of evolution that took place after the sort of basic epoch of formation early on, right? And that was like an exoplanet driven change of thinking that has also applied to the solar system. And there's a ton of models for now how the solar system evolved early on that also involved that like early evolution, right? And there was a period, so this was when, I was like a postdoc and just starting as a faculty member, where it seemed like we had a pretty decent understanding in broad terms of what was going on, right? And so you're seeing here a simulation of a planet interacting with a disk again, making these holes and spiral arms and things. And there was a famous paper from like 1980, so way back, long before any exoplanets were discovered, which was actually looking at like Saturn's rings. But in the abstract of that, they said the same processes that take place in Saturn's rings, if you applied them to planets like Jupiter orbiting the sun in the solar nebula, would imply that Jupiter could change its orbit and potentially, move much closer to the sun on a really short time scale. Okay, so you can see here it mentions like a few thousand years. Okay, and so for various reasons that wasn't actually the right answer because they didn't quite get it right. But on a few 100,000 years, it's a very much the correct answer, right? So there was a story in like the late 90s that the way you get the planets that are really close in, like the hot Jupiters that were the first exoplanets to be found, is, well, they formed out where Jupiter was, they interacted with the gas in the disk that was left over, and then they spiraled inwards, and then they eventually kind of stalled close to their star, right? And that was like the story for how you make those planets. Then there was a second kind of surprising observation, which is that when you look at, again, giant planets that are a bit further out, like a 1 AU around exoplanet host stars, they typically have quite eccentric orbits. So the eccentricities are something like 0.3 on average, something like 0.25, 0.3. Sometimes they can be 0.8. So sometimes they can be more like comets than like solar system planets. And there's a way to do that, which is to imagine you start with a planetary system that has like a ton of planets that are packed pretty close together so that the orbits become unstable. The orbits eventually cross each other, and then the planets either collide or some of them get ejected. And then what we see are the survivors, and this dynamical kind of shake-up early leads to them to have eccentric orbits. And again, we and many other people did little calculations of that, and you find that you can reproduce the distribution of eccentricities that are seen in exoplanet systems really well with a pretty simple model where you just like take maybe 3 planets or 4 planets, put them close together, let them do this scattering thing, and then the ones that are left have the distribution that is basically what you see with exoplanets. So that seemed really good. But then everything since then has just muddied the waters and made things more complicated, right? So if only observers had stopped observing at that point, everything would have been just really great and we'd have, been happy. But there were 2 things that were like really influential. So one is that at about like 2010-ish or 28, about that time, so like 15 years ago now, people were able to observe the tilt of exoplanet orbits relative to the equator of their host star, right? So you've got the star, which is spinning. That defines like a stellar equator. And then you can ask, well, are the planets orbiting in that equatorial plane, or are they tipped up in some way relative to it? And in the solar system, there's a misalignment on average of like 7 degrees between the solar rotation axis and then the plane that's defined by the planets. And what's found is that the hot Jupiters, the massive planets that are really close in, there's a bunch of them, especially around hotter stars, which can be like polar or even completely retrograde, right? And that is, let's say, very hard to understand how that situation got set up. And it certainly seems very inconsistent with the view that they just kind of sort of smoothly moved in through the gas disk, because then you expect the gas disk to be in the equator and the planets would stay in the equator. So this observation sort of shot down the idea that it was just this gas disk migration process that was responsible. And then the Kepler mission, which looked at much lower mass planets, found that when you look at multiple systems there, they seem to be close to resonances. So, you know, systems where the orbital periods are close to an integer ratio. So they're close to resonant configurations, but they're not quite there. And that remains probably the most sort of puzzling thing about the populations of planets that were seen by Kepler. And again, it's really not clear what that means, because if everything was migrating through a gas disk, you'd expect a lot of things to actually be trapped in resonance. And that's not what is observed. So, you know, what's the story here? Again, this is another one we don't know, right? And I would just say that there's an abundance of ideas out there, right? And the basic sort of ideas, well, the gas disk migration still plays a role. That's like a real process, we think, right? And so we think it should be going on. This planet-planet scattering, again, we think is going on. But then there's a bunch of other things that people think are probably important, right? So maybe in some systems there would be a binary star, and the planet might interact with the binary star in some way. Maybe that's the way you make these tilted systems. But then there's a bunch of other ideas as well. And so presumably some of these are more important than others, and presumably some or all of them, or at least some of them, were important in the early solar system. And I think on the observational side here, we're still like looking for sort of special systems that maybe can help us sort through the confusion about what is going on. But it's a difficult problem. Okay, so then let me just briefly say about one more thing, and then I'll wrap up. Which is a different observational frontier, and that's trying to find circumplanetary disks. Okay, so you know, I'm not sure who realized this first, but you know, when you read about like the Galilean satellites, the thing that almost always you read is that, hey, it looks like a miniature solar system around Jupiter, right? And so obviously someone really early on realized that, and certainly as early as Kant. The suggestion was made that the Galilean satellites sort of formed in the same way as the solar nebula, that there was a disk around Jupiter, and the satellites formed out of that disk in the same way that the planets formed out of a solar nebula disk around the sun. Okay? And the way now we think that happens is if you have a gas giant protoplanet, it's in the protoplanetary disk, it opens up one of these gaps, like I was showing in the simulations, gas continues to flow in, and it forms a disk around the planet, and that's the circumplanetary disk. So that's been known for a long time. Really exciting, just a couple of years ago, was the first detection of such a disk. And so here's the image. It's again ALMA, this sub-millimeter wave radio telescope. The system is called PDS-70. You can see there there's sort of a ring of emission. That's the outer part of the protoplanetary disk. And then there's a dot at about the 3 o'clock position. That's the location of a planet. There are actually 2 planets that are seen in that cavity. And then this planet, the one that's at the 3 o'clock position, has radio emission that is a little bit extended around it, that is apparently the circumplanetary disk. And this is the first time we've got some observational evidence for seeing this structure around another planet. So that's really exciting, and there's an expectation that, you know, as we get better observations, maybe we'll find like a ton of these, right? And that will tell us something ultimately about how planets accrete, and also maybe how satellites form, right? We've not yet found any exomoons, but presumably they would be forming in these kind of systems. And this is really exciting for those of us who are theorists, because at the moment we know basically nothing whatsoever about circumplanetary disks, right? So we've observed one, and when I say observed, like it's a pretty, you know, not a lot has been observed, right? You know, yeah, not a lot has been observed. So, you know, so things are really open. And so the sorts of questions we're interested in are, we know that when stars are accreting from their disks, the magnetic field of the star plays a really big role. So the gas disk goes in, but then at the inner part, the magnetic field of the star plays a role, and the gas actually sort of follows the magnetic field line in and hits the star on hotspots. And maybe that's how these young planets also accrete. But maybe it's also, maybe instead they don't have strong enough magnetic fields, and the disks around them go all the way to the planet and kind of join in a belt, right? So that's one thing we're looking at. We're sort of interested in how those disks are being fed. So it's sort of the gas is coming in from the protoplanetary disk, and it's forming this circumplanetary disk, but exactly how big the disk would be and whether the gas is always flowing inwards or can sometimes be flowing outwards, those are also kind of questions we don't know the answer to from a theory point of view. So these are simulations which we're doing computer simulations of fluid dynamics to try to answer that.
I just want to make the observation that this is a beautiful example of how science works. Someone who's brought up in a mainly social science paradigm, this is just a great example of how science progresses. And it isn't any great surprise that when you're starting out on this adventure, that what at first looks to be very simple over time becomes increasingly complex. Not a big surprise.
Exactly. Yeah. And so, I think that's exactly the thing, right? We know with the in the exoplanet example, right? So the exoplanet thing is kind of interesting because it's kind of something I've been able to follow sort of from the start of my career towards now, right? And yeah, it's exactly the case that some things we thought we knew turned out to be basically correct, as far as we know. But then, the observations which weren't present found completely new things that were completely unexpected, right? And then, of course, because it requires new ideas, and there's that process which plays out in this field. So we're looking at this and trying to understand what those disks maybe ought to look like. And then there's just just to mention one really little bit out there idea. You might think, well, the circumplanetary disks should be in the same plane as the main disk around the star. But actually, it turns out there's there's a possible instability that can cause one of those disks to tip up and tilt away from its from its initial plane. So these are again some simulations we did of that. You can see on the right there a disk that was initially planar, which is actually kind of tipped up and tilted, right? And maybe that ultimately could be connected to say something about the obliquities of planets. Are they actually aligned, or have they been tipped up in some way? Right? So we're looking at all these things. The main point, which goes back to that question, is from a theory point of view, the dynamics, the hydrodynamics, everything is like really rich and complicated, hard to understand. So it's really fun to look at. But the key is we need more observations, because you can only go so far by theory and simulation, right? You can never do the thing properly, and so you try to do simplified things, and then we need some observations to really guide us to where we are.
And the web is of no particular help with any of this because of the wavelength being used.
Just today I was looking at web proposals for the second cycle, all right? Because the deadline for submitting grades for them, I'm on one of the exoplanet panels, was today. The main thing that could be done with Webb is Webb can measure some chemical compositions of the inner parts of disks, right? Which at the moment we don't know very much about. So ALMA, the radio stuff, is like generally on large scales. Webb, not resolved images, but spectra, can say something about the chemistry in the inner part. So that's like really interesting for like understanding the compositions of planets. And then there's a possibility that you might be able to do some directly imaged planets further out in some regimes that are not accessible at the moment from the ground. So Webb is not super great for that, because it wasn't really designed to do that as part of the mission, right? So it's not really designed as a direct imaging exoplanet mission. But in some wave bands and for some setups, you can still do better than from the ground. So there's the possibility you might be able to find some maybe like Saturn or half Jupiter mass objects at like 30 or 40 astronomical units around some favorable targets. It's not been done yet, but let's say people are proposing to do that. And if they get the time, and then if the objects are there, there's a chance that it could be seen. So let me just finish then with a wrap up there. There's lots of things we don't know about planet formation, or at least I don't know. But I want to finish on like a positive note, which is amazing observational progress, right? So go to the NASA website, database of exoplanets. There's like 5,000 objects there. So that's like an amazing number of exoplanets that have been discovered. And then just the fact that we can image a circumplanetary disk around a young planet around another star. I mean, that's really like almost something out of science fiction from like 20 years ago or something, right? It's really amazing that can be done. And lots of new ideas. and new frontiers for the next 10, 20 years, right? So I think the excitement in like the field of exoplanets and planet formation is has got a long way to run before it becomes an old and mature and boring subject. So I will stop there. Thank you. Yeah.
Yeah, are you planning to use or write a proposal about this? Change for council?
Yeah, I mean, not personally, because I've hardly ever been involved with observations. But yeah, I mean, a lot of people are, right? And as I say, I think the main things that Webb contributes in this space, I mean, well, the main thing in total, right, is atmosphere observations, right? So that's, the two pillars, I would say, of like Webb science. One are like the very high redshift universe, right, for very distant galaxies. And then the other is transit spectroscopy, so trying to measure atmosphere properties by looking at the light from the star that goes through the atmosphere. So those are the big things we get from Webb.
Half of the news I hear about the James Webb Telescope all being with exoplanets, they discover the water molecules in the atmosphere. It's quite amazing to come to the point that they could find Earth-like planets also. I mean, they're trying to detect any atmosphere.
Yeah, I mean, okay, so I would urge caution about that second bit, right? Because I think that the basic story is like, it would require exceptional luck for Webb to be able to see anything. So the main biomarker, right, is either oxygen or ozone, right? Those are the two species that are the closest to a single molecule you can see that is an indicator of life. And to do that on an Earth-like planet or something that could potentially be habitable with Webb is really very unlikely. So that is almost certainly going to have to wait for the next generation that is currently still in the concept phase. And so we're going to have to be, we've all got to go to the gym and, I don't know, eat healthily or something to see that, because that's still a ways out, to be honest. And I would say there's a debate in the community. If you sort of look at all the exoplanets we know, right, there's only so much James Webb time, right? James Webb only has a finite mission and there's only so much time, right? So there is actually a sort of debate among like people who do that, which is not me, how much should we be trying to use Webb to sort of get an overall census of, the different kinds of planets there are out there and what their atmospheres are like, versus sort of putting all our eggs in one basket and just staring at one object that we think is the best target, right? And, it's early days, and so people haven't really quite decided what to do. But,
I think one thing you seem to leave out is the fact that the formation of a star itself is a highly non-linear thing. And supposedly with our sun that had a period of million years or so, and there sort of were very strong magnetic fields. And also very early on, things like we have sunspot cycles still from events that must have happened very early in the formation of our sun.
Yeah.
Don't you see any interaction?
Yeah. I mean, so yeah. So I mean, there's some, I mean, that's an important point, and there's some observational attempts to do things relevant to that, right? So I mean, obviously you might look for like exoplanetary aurora, right, which would be like a manifestation of that kind of interaction. The point that is most discussed in terms of sort of the end property of the planets, right, is if you have too much UV, too much X-rays early on, then that can like evaporate the planetary atmosphere. And so the particular place people worry about that a lot is arguably the easiest place to look for like biomarkers and things like that would be planets around extremely low mass stars, like M dwarfs. And those planets would be really close in because the stars are super dim. Those low mass stars are also more active in a relative sense than the sun. So that physics, the physics of stellar activity, could put a dampener on really the prospects for like habitability around really low mass stars. And it's kind of a trade-off, right? Because those planets are the easiest to look at, so obviously people are going to look at them. But I think there is a feeling we don't want to put all our eggs in the basket of just going for low mass stars, because yeah, maybe in fact the sun-like mass is more favorable.
Computer hardware question. Do you feel computer hardware is advanced to the point where it's no longer a limit on your work? I think you have simulations that you don't run because it would be months of time.
Yeah, no, I mean, definitely it's still a limitation, right? So, and so, you know, there was one simulation I briefly flashed up there involved like, you know, doing radiation transport. And so at Flatiron, we have like one of the world's experts on that. And we have, I think, you know, probably some of the best simulation code to do that. But those calculations are tremendously expensive. So, yeah, there's only so much you can do, and anything more would be better. And there's a move to do more on GPUs, and that's, you know, that's the main way that people are going to do things faster at the moment.
I just wanted to say how much I enjoyed your approach to this. When I saw the title at the top of What We Don't Know, fascinated me, because usually when you have these kinds of discussions, it's, and here's how the planets formed, and here's how the stars formed, and you really, you know, the idea that there's so much that we don't know, and taking a look at the various approaches that we're trying to, well, maybe it happened this way, it did, but then it falls apart here. I really just very much enjoyed the way you approached it. Thank you very much.
Thank you.
Have we ever looked at, we know a lot about our solar system and about the Earth and so forth. Have we ever basically tried to do a map of what people with our equipment that we look at everybody else with would see at different distances? Because that would help us inform what we might be missing.
Yeah, I think people have sort of tried to, you know, make that thought experiment, right? You know, with our current technology, you know, if you looked at the solar system with like radial velocity measurements, like we use for like a lot of exoplanets, right?
From different distances.
Yeah, you know, you would not see the Earth, you wouldn't detect the Earth, or it'd be very difficult to detect the Earth. You would detect Jupiter, and that would be basically it. Right?
Yeah, so basically, what we don't see could be enormous.
Oh yeah.
Compared to what we do see.
Yeah, for certain.
So I think one of the first comments has been very true, that everything is sort of slanted to the fact that yes, if something is a dust cloud and a great distance around the star, we can see that. If there's a Jupiter object that's really close to the star, wow, we can really see that. But there may be so much.
Yeah.
That's there right now.
Yeah. And, you know, I think, you know, the example that I think is like super important, which is very much to this, right, is that, you know, NASA's Kepler mission was, the design of the mission was intended to measure the frequency of Earth-like analogs around solar-type stars, right? That was the whole goal of Kepler, right? And Kepler was tremendously successful and discovered thousands of planets, right? But for various like technical reasons, you know, the noise level was a little bit higher than expected. And then even though the mission was extended, the reaction wheels didn't have they had a long lifetime, but they eventually broke. You know, it did not actually manage to really answer that question. So, you know, we still don't really know what fraction of stars have things like the Earth in Earth-like orbits. And actually there's nothing in the immediate future that's going to actually solve that problem, right? So that's a, you know, for this question of habitability, that's a big problem. You know?
We seem to be concentrating very much on things that are far away off, because we're trying to look back in time, very far. And at the same time, most of the things that we're interested in relative to our formation on Earth could best be seen from close up.
Certainly.
Concentrated there.
Yeah, I want to follow up on kind of what he was saying. Given the technology we have now to view the exoplanet, somebody in another galaxy is looking at us, given the configuration, would they be able to see Jupiter or Saturn? Cause the same?
I mean, yeah, I mean, so you know, so this is an interesting. This is like an interesting question, right? And you know, there are lots of papers on it. Right? So you know, first of all, you know, in another galaxy, it'd be very hard to do anything, right? So you really got to think about like the Milky Way. They're in the Milky Way, yeah. You know, I mean, yeah. Today, with like exactly our technology, right? They could see Jupiter from like the radial velocity effect on the sun, right? They could see the Earth if they happen to be in the plane such that the Earth transits the sun, right? Otherwise, they'd be in trouble, right? You know, yeah. You know, I'm kind of cautious about, you know, sort of going too far with that argument, right? Because, you know, technology advances so quickly, right? So, you know, the missions I was talking about that might like measure the atmospheric properties would also be able to directly image the Earth, right? And, you know, technology-wise, we're like 15 years out from being able to do that, right? Now, whether it really takes 15 years is, you know, a matter of like NASA budgets and stuff like that. So it's questions that are beyond technology and science. But, you know, we're not too far from being able to do that, right? And so that, you know, that window where we have this particular technology is like, you know, vanishingly small in the grand scheme of things. So, you know, that's, yeah.
As you study the formation of exoplanets, is there a point where, as the particles are being swept together, that you recognize a point where the mass has stabilized, or is it in continual development?
I mean, I think the way I would tend to think about it, at least for like rocky planets, right, is sort of in terms of kind of the system is trying to find a sort of quasi-stable state, right? So if you have a certain amount of mass and you put it in, you know, a certain number of bodies, right? As the number of bodies gets smaller, the stability of the system gets longer, right? And so, like, roughly speaking, at any time, the system you expect to be sort of stable for the amount of time it's lived, something like that, right? So it's not like a sharp cutoff, right? It's not like, okay, at this point things are still growing and then later they're not. It's just things are getting more stable, and at some point they become like effectively stable for as long as you care about, right? I mean, the exception to that would be something like the asteroid belt. Right? So the asteroid belt has gotten stirred up by Jupiter, and so now the asteroids have quite eccentric orbits, and so when they hit each other, they break up into small pieces again. So in the asteroid belt, everything is now going, you know, the opposite direction, right? So definitely nothing's growing there. But for the other planets, it's more of that kind of, yeah, it kind of grows and then it kind of becomes stable. And that's really just a gravity thing, right? You know.
I find it very unusual of many exoplanets orbit inside of Mercury's orbit compared to our solar system. And you find that unusual or pretty much common? I mean, a lot of exoplanets that orbit inside of Mercury compared to our solar system.
Yeah, I mean, observationally, it is super common, right? And I think it's really surprising. I mean, you know, I still think it's surprising, right? I mean, there are understood ways in which it could happen and probably did happen. But yeah, it's a big puzzle. And you know, there are famous systems where, you know, you see two planets that are really close together in the same star, right? And one of them has we don't know much about what they're made of, but one of them has a density that's really consistent with just rock, right? And the other has a density that implies a lot of hydrogen and helium. And yet those two objects are like, you know, right together. So it's as if in the solar system we had like Earth sitting here, and then, you know, we're closer than where Mars is, you know, we had something with the composition more like Neptune, right? And, you know, that's, yeah, that is, you know, one can come up with theories of how that happened, but basically it's still a really puzzling observation, you know.
Days, weeks,
exactly.
Years.
Yeah.
Would that be a function of how long we're willing to look at any one object to see if there's a light change or a velocity change? Because the time that we assign ourselves to look is so precious to us. So if you look at a particular star.
Yeah, I mean, I think you know the point there is that, you know, there is this clear selection bias, right? That, you know, looking for things at certain radii, so, you know, things really close in are easy to see, things really, really far out are also relatively easy to see. The range in the middle is the tough thing, right? Because that's the place where the indirect ways of looking for exoplanets are really hard, and they're too close, they're still lost in the glare of the central star, right? So there is this real selection effect. You know, what is sure though is, you know, there are some kinds of planets that are super common around exoplanet hosts, which we don't have in the solar system, right? So in that sense, there's no selection bias there, right? We don't have anything inside Mercury, and we don't have anything that is like 4 Earth masses in the solar system, and 4 Earth mass planets are actually really common in the universe. So, you know, so it's of interest that we don't have that stuff in the solar system.
For the systems we're able to observe, how many decades or centuries would we need before we actually noticed any change in the, like, to see if these systems are actually evolving? It would take centuries, right?
Yeah.
Because
There's almost no hope of doing that, right? The only thing, you know, that maybe can be observed or has been observed, right, is that at a bit of a later state, you know, imagine like the moon forming impact, right? So, okay, it only happened once, but, you know, let's say, you know, it happened, and then the moon probably formed on a time scale of like thousands of years. So like a short time scale, right? But, you know, okay, 1,000 years, you multiply that by 1,000,000, you get 1 billion, right? So if you, you know, you look at 1,000,000 stars, right, you might get lucky and, you know, see such an event, right? And okay, so, you know, that particular thing has not really been seen, but there are debris disk systems which appear to have like a lot of luminosity, a lot of dust, and it's suggested pretty reasonably that, you know, there may have been a recent giant collision in those systems. So I think, you know, let's say technologically it's not infeasible to imagine a relatively near-term future mission that like stares deeply at the whole sky all the time, right? And you might see a small number of those kind of things, right? And that's the best you can really hope for.
Well, it's something to consider, right? Because you're not really looking at one whole system. It's an algorithm that's scanned.
Yeah, you've got to take advantage of the fact that you've got to look at everything, right? Yeah.
So it's the algorithm that's better.
Stop the recording. I think you were the one that had to start it.
I think I just permitted it to be done. So I think you stop it actually.
you started it, Candy.
You started.
Oh, somebody said that.
Or
Yeah, I just had to say it was okay with me on my screen.
Oh. I don't know what happened.
or perhaps.
Oh, pause, stop recording. Okay. Okay. So